All right, surface area. The formulas that you need to know for this. Remember, surface area is not volume. Volume is if we're filling this box or this box with water or sand or toys or whatever. Surface area is if we are painting the outside of it with paint. How many square inches of paint as opposed to cubic inches? How many square inches of paint on the outside as opposed to how many cubic inches of paint would we need to fill the thing? So surface area, the big trick with surface area is that you have to not miss any sides. A cube will have 6 sides, like a little die, you know, from dice. So, you know, that may help to remind you. Typically, solids will have the opposite sides will be the same, but they won't always. You may have a bizarre, complex shape that has all sorts of different sides. You still have to remember to count all of them. So the surface area of a cube is just the surface area of one side. So if we were just going to paint one side of the cube here, that would be S times S, length times width. That's the area of one side. But there are 6 of those sides, so it's actually 6 times S squared. One side is S squared, 6 of those is 6S squared. The surface area of a rectangular solid, that's where it gets trickier, right? Because the sides aren't all the same length. So we have to remember to match up each of the sides. So there's, you know, we could do this one side. This one side here is the width times the height. That's the front. I've decided that's the front. So width times the height. But remember, there's this side, and then there's the one exactly like it on the back of the box. So we actually need 2 times the width times the height. Plus 2 times the length times the height. This side over here on the side, and the one matching it on the other side of the box. And it just wouldn't be a party if we didn't do the top and the bottom. So we also need the length times the width. But again, since there's a bottom and a top to the figure, we need 2 times that. So because the sides are all different lengths, we need to account for all the different combinations of their individual surface areas, double them because there's one on each side of the box, and add them all together. Okay, so here's a practice problem from our secret storage warehouse of problems. Cube M's side length is 3 times longer than the side length of cube N. What is the ratio of cube M's surface area to the surface area of cube N? Okay, so we don't actually have to draw the cubes, although you certainly could if you wanted. So let's say we have cube N here and cube M here. One side, we'll call cube N's side N, and cube M's side length is 3 times longer. So it's 3 times N. So from there, then we know that one side's area, remember that, you know, when you have a cube, one side is just side squared. So this would be one side's area would be N squared for N, for cube N, and 9N squared for cube M. What is the ratio of cube M's surface area to the surface area of cube N? So the surface area, remember, is 6 times this. So, but before we go crazy multiplying that out, what this question is ultimately asking for is their individual surface area is 6 times 9N squared over 6 times N squared. We don't even have to multiply 9 times 6. These 2 guys are going to cancel out. These 2 guys are going to cancel out because they're both N squared. We're left with 9 over 1. There you have it. Finally, the surface area of a cylinder, one of the hardest ones to kind of visualize. I find it very helpful to think of a soup can when I do this. So the surface area of a cylinder is basically made up of the same pieces of tin that you would need to make up a soup can. You need 2 circular pieces. Remember that the area of a circle is pi times the radius squared. So you're going to need 2 times pi times the radius squared to get the circular top and the circular bottom of your tin can. What about the rest of it? What about the sides? Well, think about what the wrapper on a soup can or on a soda bottle or something like that is like. When you unwrap it, does it come out like a circle? No, it doesn't. When you unwrap a soda can, when you get, you know, or, well, soda cans don't have wrappers, but when you unwrap a soup can, you end up with a rectangle. It's a rectangle that's been wrapped around a circular object. The area of a rectangle is just length times width. I guess I should make this the width and this the length. And it's the same way for something wrapped around a cylinder. The problem is cylinders don't really have a length, do they? So the width of a cylinder, so imagine this thing has been, wrapped around this can here. The width here that we have is the same dimension as the height. I'm imagining that we placed this next to it and, wrapped it around. Anyway, so the width is the height. So the area of this guy is going to be h. Now what's the length of this wrapper around our can? It's the same as the circumference of the circle, right? So, and the circumference of the circle is 2 pi r, so it's h times 2 pi r. So length times width becomes height times 2 pi r. It's still a rectangle, but we're expressing those two dimensions using the terms that come from a circular shape or from a cylinder. So 2 pi r squared for the two circular ends of the tin can or the soup can, plus 2 pi r h for the rectangular wrapper that goes around the shape. That is the surface area of a cylinder. So if you just remember the two, what pieces you would need to make one of your own, that might help you remember it.